Let me kill the lights so you can see this. All right, so this is, yeah, that's not that easy to read. So in the orange are the grades on the exam that you just took with an 11.7 point curve. Now that, I'm not a big believer in curves. So that curve comes with conditions, and the conditions are going to be that I'm going to return the test to you and that you must correct two problems and turn those into me a week from today. All right, so that'll be due next Wednesday. So you get to pick which two problems to correct, but they need to be ones where you got a significant number of points off. So, you know, don't pick the one that you got -1 on. You know, it's got to be something. I want you to go through a problem that you couldn't get while you were sitting here and go home and get it, all right? I don't mind if you talk to each other about it, because it's more important that you understand it than it is that, you know what I'm saying? Yeah. Okay. So these are the grades with the curve in the orange. So the highest grade was a 106.7, and the lowest was a 42.7. Our average was a 70 after the curve, so it was about a 68-ish, 68.3, I think. So I curved basically up to make the average grade passing. That's the way I did it. Our standard deviation was 18.5, which is, y'all know what standard deviation is? It's how spread apart the numbers are, the grades. So that's a pretty big spread. It's not, I've seen it in the 20s a few times. I've seen it as low as 12. I usually see it around 15 or so. So, okay, it is what it is. Now, the blue with the red, that's a student who's done one of the mini exams or two of the mini exams. It's their average on the mini exam. So, for example, like the student who got the highest grade on the test also did at least one mini exam and had a decent grade on that. And then this student who had a high grade has done at least one mini exam and has a high grade. And this student did pretty well on the test, has not turned in a mini exam yet. So I don't see much correlation. I don't know, maybe like this group is still kind of like what they're doing at home is kind of close to what they did on the exam. You can interpret this different ways, but that's the data. This is the A's, B's, C's, D's, and F's, so this is not fun to look at, but it is what it is. Yeah, so I think the test was challenging. I think the grades reflect that, but there were students that did well on it. So, yeah. Any questions or comments or concerns or complaints or gripes or anything about it? I think, what I should have done, I think, in retrospect, I should have told you to like skip the first three and just go back to those at the end, because I think the first three could get you really bogged down on that test. And maybe if you had done the ones at the end first, you would have had more, energy in the beginning and then got back to the other ones. But I almost said that, but I just was like, let's see what happens. All right, yeah, we move on, right? So I will hand these back at the end of class. That way, right now, you're more focused on what we're doing. And then, like I said, a week from today, you correct two problems. I'll give you the option to do 3 for another 5 points, all right? Make sense? Now, some students, the reason I don't like curves is because how do you curve? Like how would you curve? Do you curve? Like a curve implies there is a curve, right? Yeah. I don't believe in curves because it's not fair to curve someone who didn't do well more than I curve someone who did do well, right? So like I can have Canvas where we have our grades, I can have it curve for me, and it curves the average to a 70, but some people, like these people over here only get like 2 points, and then people over here get like, 15 points, and that doesn't make any sense to me. But if I'm going to offer this correction type thing for these bonus points, then obviously the student like the students here, I can't give you like 120 on the test. You know, it's just like, I think you're kind of maxed out already, so you don't really need to do any corrections. I know that you can say that's not fair, but I don't know. It's tough, right? I'm trying to help, but it wouldn't make sense to give someone 120 on a test. All right, we move on. So last class we were talking about finding the maximums and minimums. Do y'all want to keep the lights like this, or do you want me to turn on some lights? Oh, the mini exam. Yeah, if you did the next one, congrats to you for getting that squeezed in. Did you do it also? Yeah? Okay.
Number 3, right?
Yeah, the mini exam 3, yes. So do y'all want the lights like this, or
I'm good. I have this light right here.
like we can do that? Or are y'all feeling sleepy today?
I might actually
Sleeping every day, yeah. Okay, I'll just leave it like that. All right, so last time we were talking about, well, basically what we have at this point is that if somebody gives us a function of 2 variables, a surface, we have a way of finding the absolute maximum and minimum values of that surface as long as we're on a closed bounded set. Or if we're not on a closed bounded set, then we can find local maximums and local minimums using that calculation of capital D. Okay, those are the 2 things that we have. Now on the test that you just took, we only did a problem that had capital D on it. We didn't have a problem that had closed bounded set. So that will be on the final. And we did a few examples, and the last example in this section is the one I want to start with today, and that is this problem here. I know that's kind of small, but I'll read it. It says, find the volume of the largest rectangular box with edges that are parallel to the axes that can be inscribed in the ellipsoid with the equation given. So we have this ellipsoid, this egg-shaped thing, and we want to know if we try and inscribe this rectangular box inside of this ellipsoid, what's the most volume we can possibly get out of that box. Now, inscribed means that it touches the surface of the ellipsoid. So it can't break through the egg, and it can't be inside the egg without touching, right? So what we're going to do right now is we're going to set this problem up, and we're going to look at what it would take, and then we're going to go, shit, that's going to be a lot of work, and then we're going to move to the next section, and then we'll be able to do this a lot easier, all right? So let's try and see if we can't figure out how to do this. We are trying to find the largest box, right? So, well, we're trying to get the most volume out of this box. So we're trying to find a volume function and maximize it. So how are we going to get the volume of this box? How do we get the volume of this box? Well, what is the volume of any box? Like if we have some sort of 3-dimensional box like that, what's the volume of any box like that? Length times width times height, right? So the volume of any sort of parallelepiped, that's what they're called, length times width times height. So maybe we can somehow look at this shape and figure out a way that we could determine the length times width times height. Right now, the volume depends on 3 different things, right? It depends. You'd have to give me a length and a width and a height for me to be able to tell you what the volume is. But the only thing we know how to do right now is find the maximum and minimums of functions of two variables. So the most that we can handle is if we have something that depends on two things, we can find max and mins. But if it depends on three things, we don't have a way of doing that yet, right? So maybe there's a way we can break this volume function down to depend on just two things. So one I guess, perspective here is that if we look at this box inside, see that black point? That black point is going to be, let's say, in our first octant. So it has, to get to that black point, we come out on the x-axis some distance, we come out on the y-axis, and we go up to some z point, and that point actually lives on the ellipsoid, right? Right? It lives on the ellipsoid, so it must satisfy the equation of the ellipsoid. Its x and y coordinates, on the other hand, are free, somewhat. I mean, they can't just be arbitrarily anything, or you could punch out of the ellipsoid, right? There is some restriction on that x and y. So let's see here. If we were to go out x, go out y, and let's just call this z, okay? So we have x, we have y, let's call that z, then what is the relationship between this box and the volume of the entire box? So this has, let's say, some x here, some y here, and some z here. The volume of this thing would be x, y, z, right? But that's only 1/8 of the whole box in the ellipsoid, right? Agreed? Because it's only in the first octant. So when we're looking at our entire box, we actually want to look at the volume as being 8 of these things, right? So our volume that we're trying to find the maximum of right now is a function of three variables, x, y, and z, and times 8 because of the picture, right? So how do we get this to a function of just two variables? What can we do? The key is the z. That z coordinate, right, must land on the ellipsoid, right? So that z coordinate must satisfy the equation of the ellipsoid, which is this equation right here. And that means I can take this and solve it for z, right? If I solve this for z and replace that here, I will have an expression that has just x's and y's in it, won't I? Okay, so let's do that. Don't think I need this picture. Let's leave the problem there. Does everyone understand what I'm doing? Are there any questions on what I'm doing? Okay, so let's solve that. Solve that for z. So let's go. 4z squared equals 36 minus 9x squared minus 36y squared. And then I'll divide everything by 4 and take the square root. So what, 9 minus 9/4 x squared minus 9y squared. And technically this should be plus or minus because I took the square root, but because we are looking at that little box in the first octant, I'm just going to be taking the positive. So now here's where we are. We have that our volume, the volume of the thing we're looking for, the maximum of, is now a function of just two variables. It is 8 xy times the square root of 9 minus 9/4 x squared minus 9y squared. That's the volume function. You give me x and y, I give you the volume of the box that's inscribed, right? So we've got it to a function of two variables, but now we need to determine, are we on a closed bounded region, or are we doing the capital D? So what do we have here? We're closed bounded because that ellipsoid, if you look at your, right, the ellipsoid that's here, if you look at the xy plane, right, our x's and y's have to live inside that, don't they? You can't go outside that. So we are on a closed bounded region, and that closed bounded region is an ellipse. In two-dimensional space, it's an ellipse. So we're trying to find the max min on a closed bounded region, which is the ellipse that we get from letting z be 0 here. And so at this point, I think I'm just going to wave my hands and say, okay, this is going to be difficult. Would you agree? Because we know that on the ground, x, y, we have some ellipse here, right? We know that to do this, we first have to look on the inside, which is we have to go like almost do what we did for capital D. We have to take the partials, set them equal to 0, and figure out if there's any critical points in here. Once we figure out what's going on in here, then we have to move our way around the boundary. And that boundary motion is going to be difficult because it's not straight lines, right? So this is going to be tough. But it could be done. It's just going to be an algebraic nightmare. Not only that, do we really want to take the derivative of this, right? Like, do we want to take the partial of that with respect to x twice? You know, well, no, we won't need capital D. So we only need it partial with respect to x, partial with respect to y, setting those equal to 0. Doesn't that seem like a nightmare? Okay. So can we at least appreciate the challenge of this problem? Okay. So let's put it on the back burner and let's start the next section. All right, so the next section, I think personally is one of the more challenging sections, and because it's going to require some logic and lots of algebra. It's called Lagrange multipliers. So remember, we're back burner, right? We're back burner on that problem, right? Way back burner. We're going to start here kind of from scratch. So here's the idea behind Lagrange multipliers. It's another way to find maximums and minimums of functions of two variables. But what's better about this method is that this method extends into functions of 3 variables, and 4 variables, and 5 variables. We will only stick to 2 and 3, that's it, okay? But it can be extended. So I want to show you visually first what we're going to be doing. So let me get to the problem. So here is a surface, right? Here is a surface. It's this paraboloid. And what we'd like to do is find the max and mins of this surface, but we want to restrict the domain. This time we don't want to do a closed bounded region. What we want to do is a closed or just any curve. So imagine that I say, okay, you're only allowed to take points in the xy plane that live on that little circle, all right? So this is your domain, and just those points are allowed to be pumped into the function. Then when we put those through the function, you're going to get some sort of curve that lives on that surface, right? And what we're trying to do here is we're trying to say, okay, with that curve up on that surface, what are the absolute maximum and minimum points? Right? So it's very much like what we've done in the past. You remember how we moved around the boundary? This is pretty much going to allow us to take care of the boundary part with a new method. Now the inside piece, we still have to do the old way. We have to, set the partials equal to 0 and find critical points. But this way is going to allow us to do this piece with this very amazing method. All right? So that's where we're headed. Let me give you another visual example of this. Give you a different one. Okay, so here's a surface, all right? We have this function e to the xy, and this time we're only going to be allowed to plug in points that live on this curve. So our domain, again, is on the ground. Okay, so this is the domain, and you're only allowed to take those points and plug them up into the surface. And that's going to generate some curve on the surface, right? So here's your curve. let me pull the surface out. I'm going to pull the surface out completely, all right? And so you can see the points on the ground are being plugged in, and do you see how when they go into the surface, they create this black curve? We're trying to find the maximum points in minimum, so that it corresponds to that point right there. Make sense? Yeah. Now, this is not a closed bounded, right? Like, this is not a closed curve. This method works for any curve on the ground. It can be closed, it can just be a curve going around, doesn't matter, all right? All right, is that enough visual to give you an idea of what we're trying to do? Okay, yeah? All right, now the method. Let me show you, I'm going to show you the formula, but I'm going to try and give you sort of a visual. This is in no way a proof. This is just a visualization of where this method comes from. Okay. So, first of all, we have some surface that we're given, right? Some surface we're given, and then we have to figure out a domain on the ground. That domain on the ground has to be some function of two variables equals a constant. So in other words, if I give you that, that's a surface, right? But if I set it equal to a constant, then what we're doing is remember those level curves when we were first talking about surfaces? Like when we try and graph surfaces, you have to like set one of the variables equal to a constant and then draw something. And like you had, like an ellipsoid, you had cross sections were ellipses. Okay, this is the same idea. This right here is our constraint. Or in other words, the domain, all right? This is the domain, all right? So our domain, let me give you a specific example. X squared plus y squared equals 9, right? This would be, look, you're only allowed to plug in points that live on a circle with a radius of 3 on the ground, right? Okay. Now here's the thing that's amazing about Lagrange. The way this method works is it says, okay, look, great. You have this constraint which dictates what your domain is. Take a look at just the left side without equal to a constant and look at that surface. Just look at that surface right there. This right here is a specific example of a surface. Now it's not this one, but this right here is what you're seeing in orange, okay, is just that surface. If I restrict it to a constant, then what I get is just one level of that surface, okay? All right. Now, I'd like to show you a vector on this surface, and we're familiar with this vector. It's called the gradient. Okay. You know what? Can we kill the lights all the way? Let's kill them all because it's hard to see this. So do you see that for this surface, which is just the left side of our domain constraint, looked at as a function of two variables, when we restrict it to a constant, we get this one level of it. And if we take the gradient, then it gives us this vector. Y'all see the vector? I'm going to look at it from the top. See that? Okay. That vector, it's a three-dimensional vector, but it's flat, all right? And down here, I don't have it there. I have the same picture, so there's the domain right there, but I've basically projected it down to the XY plane so you can see it a little better. There it is from the top view. And there's the gradient from the top. Does that all kind of make sense? Do y'all see that picture? Okay, so you're probably asking, what's the gradient have to do with any of this, right? Okay. So, I'm going to take all this shit out of here, okay? Here's our domain, and here's the gradient vector of the domain. Now, let's take a look at the surface that we're supposed to map this into, which is a completely different surface, right? This is just the domain constraint, and there's a surface, there's a level of it, and then there's a picture of the gradient. So here comes the surface I'm trying to find the maximum and minimum of. So I know it looks kind of like it's the same, but it's not. Do y'all agree? These are two different things? Yes? Okay. So now, what we're saying is, if we take just the points here and map them into this surface, where are the max and mins? So let me go ahead and plug those in. So those points have now been plugged in, so we get this blue curve. And here are the max and min points. I'm going to pull the surface out a little bit. You see our maxes? Here's our two maxes. Here's our two mins. Right? Now, let's take a look at the gradient of this surface, the one that we're interested in. Right? Let's take a look at the gradient vector of that one. So you see the gradient vector there? I'm going to show you that. See it down here? That's top view. So you see the gradient vector here of our blue, which is coming off the surface we're trying to find the max and min of. We have the gradient vector that came from the constraint. And now check this out. I'm going to move. I'm going to start moving. And I'm going to move myself to different points. So that's too much. Right there, okay? Right there. The vector kind of came out, but I'm not at the maximum yet, am I? Come down here, take a look at the two different gradient vectors. See them? Now I'm going to move, and let me get to that maximum point. Whoa, what happened? I think I'm there. I think I'm pretty close to being at the max there. Let me come down. Oh. What happened? What happened? The gradient of this thing, right, is parallel to the gradient of the surface I'm trying to maximize. So at the maximum point, our two gradient vectors are parallel, right? Let's move to another one. Maybe it was just a coincidence. Let's move to another one. Not quite getting there. There we go. I think we're there, right? Let's look at it down here. Look at that. Gradient of the domain, gradient of the surface we're trying to maximize. Right? And this is not a coincidence. We can move around, and as long as we're at a max or a min, our gradients will be parallel. They don't even have to point in the same direction, actually. All right? Parallel, remember, two parallel vectors can point in opposite directions, as long as they're scalar multiples of one another. So that means that if this is true, now again, this isn't a proof, I'm just showing you like, look, something is happening here, right? There is a proof that shows that the maximums and minimums of a function of two variables constrained to an equation like this, the maxes and mins must occur whenever the gradients are parallel. And that is the Lagrange multipliers method. And so now I will present to you the actual method. We can turn the lights back on. Just the two on the right side. Yep. Okay, thank you. So here's the method. It says that, well, this is what we already learned how to do. I already talked about that. All right. So given a function of two variables, subject to a constraint, g of xy equals k, like this, subject to some constraint equation, then we will do the following to find the maximum and minimum values of the function f. We have to figure out all values of x and y and this new variable called lambda, such that, number one, this is true. So what is this first thing, this first condition that has to hold saying? The gradient of f must be equal to lambda times the gradient of g. What is that saying? The gradients have to be scalar multiples, which means the gradients have to be parallel, right? So this is that first condition. Look, we're looking for anywhere where the gradients are parallel. But at the same time that this is true, we must make sure that the point that we're looking at still satisfies this equation. That means that it's still in our domain. As long as these two things are true, then we have our candidates for where our maxes and mins are going to take place. All right? After we figure out all the x's, y's, and lambdas that make these two true, all we have to do is evaluate our original function at those points and then just compare them. And the biggest one will be our max, and the smallest one will be our min. All right? So I hope that that visual, like, at least aids a little bit in kind of understanding where this comes from. But at the end of the day, like, this is it. This is Lagrange right here. Now I go a little bit further into this because we need to remember what the gradient means. So what is the gradient? That first equation, when we are setting the gradient of f equal to the gradient of g, the gradient of f is a vector. It's just the components are just the partials with respect to x and y respectively. We have to set that equal to lambda times the gradient of g. And so the only way two vectors can be equivalent is if their components are equivalent. So I have to set that equal to that, and that equal to that, and that comes down to these two equations. So the first condition creates two equations for us. And then the third condition, which is this constraint equation being true, gives us a third equation. And that means we'll have 1, 2, 3 equations, and we'll have 3 unknowns, x, y, and lambda. So 3 equations, 3 unknowns. The problem is the equations don't have to be linear. So you can't use matrices to solve like a system of equations. These are not necessarily linear. These can be nonlinear equations, and that's when things get messy. So when you see me doing these problems, the way you're going to see me set them up is as follows. I'm going to write out everything. You know, the problem's going to be presented, and then I'm going to create my 3 equations. And then I'm going to go try and solve them. All right? You all ready to do one? Here we go. Find the maximum and minimum of this function, x squared plus 2y squared, constrained or on the unit circle. So we have some surface. Here it is. We're only allowed to plug in points that live on the unit circle. Those get mapped in. We're trying to find those points, okay? That's what we're trying to do. So let's interpret all of this into the Lagrange. So just to be clear, in this problem, f of xy is what we're trying to find the max and min of, is x squared plus 2y squared. What is g of xy in this problem? X squared plus y squared, period. Done. Okay? That is our constraint, but it's just, see, do y'all see that this right here looks like g of xy equals a constant, right? Okay, so we have, that's our g of xy, and what we need to do is we need to satisfy 2 things. We need, first of all, that the gradient of f is equal to lambda times the gradient of g. And then the second thing we need is that g of xy maintains the equality, this equality right here. So those are our 2 things we have to make sure happen, right? So we're going to set up our 3 equations now. But before I set them up, don't I need to get the gradients? So let's do the gradients. All right, let's do the gradients. So what is the gradient of f? It's a 2-dimensional vector. What is the gradient of f? 2x is the first component, and then 4y is the second component. And then we need the gradient of g. And the gradient of g is 2x, 2y. All right, so that's just some little ancillary work that we do in the beginning. And now I'm ready for my 3 equations. So equation 1, equation 2, and equation 3. So equation 1 is that I need the partial of f with respect to x, that's this piece, to be equal to lambda, some multiple of the partial of g with respect to x. So all I'm doing is I'm equating, not equating, but I'm saying that those have to be scalar multiples of one another, right? Those components. And then my next equation is that these 2 have to be scalar multiples. So my equation 2 is 4y must equal lambda times 2y. And then my last equation is what? Yeah, I have to make sure that the original constraint is satisfied. I got to make sure that the points I find that satisfy these also live in the original domain, and then I'm in business, all right? There we go. 3, wait a minute, why didn't I write, I never wrote this down, sorry. 2x equals lambda times 2x, right? Okay, I never wrote that down here. This was partial of f with respect to y equals lambda partial of g with respect to y. All right, 3 equations, 3 unknowns. Like I said, this is the algebra time. So, how would you like to solve that?
Have lambda equal to a variable of either x or y.
Having lambda equal to a variable x or y, is that what you said?
Yes, of either x or y, you basically choose. For example, if you have 4y equaling lambda 2y, you divide 2y by that, so you can get 4y over 2y equaling lambda.
So you could solve this for lambda, is that what you're saying?
Yes.
Right? Okay. You can solve that one for lambda, right?
Yes.
Okay, that might get us there. So this is where I said algebra, right? This is critically important stuff at this juncture, all right? If we try and solve this for lambda, how do you intend on doing that? You just told me how to do it. I do what?
You put lambda by itself, and you put lambda by itself equaling to the variables of either x or y on the other side.
But okay, you told me to take this and divide both sides by 2y, right?
Yes.
Okay, so that part right there is dangerous. Why is that dangerous? Why, if you're going to solve this for lambda, why is dividing by 2y not necessarily a great idea?
Because the lambda won't be the same throughout the equation.
Let's go back to this. Let's go back to like college algebra. Solve this for x. How would you solve that for x? Someone will tell me I can divide both sides by x. Someone's going to tell me that. Maybe not in here, but someone will tell me to divide both sides by x. And when this happens, what happens over here? You get x, and here you get 4. And is 4 a solution to this? Is this answer a solution? Yes. Is it the only solution? What solution am I missing? 0. Why am I missing it? Because I divided by x, right? And whenever you divide by a variable, there's supposed to be a little asterisk over here that says, I promise x will never be 0, right? Because you're dividing by something you don't have control over. So when you divide it, you better make sure you say, hey, look, I still need to consider the idea that x is 0. This is a subtle thing, but it's an important thing. The proper way to solve this is to move everything to one side of the equation and factor. Now you pick up both solutions, 0 and 4. All right, so the moral of the story is, if you're going to be doing algebra in here, if you decide to divide both sides by 2y here, you have to include that asterisk, and then you have to go look at what happens when y is 0. You cannot forget that, all right? So my recommendation is to try not to multiply or divide both sides of something you can't control, that something has a variable in it. All right, so let me back up. Let me do this. Let me work with equation 1 real quick, since this is our first problem. Let me work with equation 1. I'm going to work with equation 1. I'm going to move everything to one side. Okay? Now, from that I can factor out a 2x. And what does that tell me about equation 1? It can only be true if what? If x is 0 or lambda is 1, right? X must be 0 or lambda must be 1, right? So our goal, remember, don't lose sight of this, is that we must find an x, a y, and a lambda that satisfy this, this, and this simultaneously, all right? So we are saying right now, in order for this equation to be true, right, one of these two things has to be true. Okay, so where do we go from here? There's kind of different paths you can go. Do you want to do the same thing for the second one? Let's look at equation 2. For equation 2, if we move everything to one side, we get that we can factor out a 2y. We get 2 minus lambda equals 0. And this says that y must be 0 or lambda must be 2, right? Okay. And then our third equation, you can't solve that explicitly for x or y. You could only get x in terms of y or y in terms of x. So I actually have 4 different kind of scenarios now I need to run through. All right? I'm going to run through each scenario. And this is what makes the Lagrange problems hard to do and freaking really hard to grade, because I have to make sure you've run through every possibility. You can't leave one of them out. If you leave one of them out, that could wind up being where you have parallel gradients. Okay, so let's take case 1. Suppose, that's the symbol for suppose. So suppose that x is equal to 0. All right, if x is equal to 0, equation 1 is good, right? Equation 1 is good if x is 0. All right, so if x is 0, that one's good. So how am I going to make the second one true? Well, I have 2 choices, right? So let's go with this one first. So I'm saying suppose that x is 0 and y is 0, right? Wouldn't that satisfy both the first 2 equations? Okay. So it's looking like 0, 0 might be a point that I get from Lagrange. But what? It's not going to satisfy the third equation. If I go to my equation 3 now, right? If I go to equation 3, I would get 0 squared plus 0 squared equals 1, which it doesn't, and therefore it fails. So I can't have both x and y 0. All right? So let me try something else. Suppose x is 0. That gives me equation 1, right? Now the only other option for equation 2 is to let lambda be 2, right? Lambda is 2. That will satisfy equation 2, right? Does it have any impact on equation 1, lambda being 2? Think about this. Look at it right here. If lambda is 2, it doesn't matter because x was 0, right? So it's still going to be 0. So we're still good on that. But now we don't have a problem with equation 3, do we? We have from equation 3 now, we have that x was 0, so 0 squared plus y squared. I haven't locked y down yet, must equal 1. And that gives me 2 solutions. Y can be plus or minus 1, right? So from this thought, we ran into a dead end. From this thought, our conclusion is that we could have 0, 1, 0, 1, and we could have 0, negative 1, right, for x and y. Now, a lot of times books and authors will have you not only find the x and y and put it in an answer, they'll have you write down 0, 1, and then they'll actually have you write down lambda too. So they'll have you write x, y, and lambda. And so these are your x, y, lambda triples that satisfy all 3 equations. The reason I don't like to write this down is because I don't want you to think that this 2 has anything to do with like the z coordinate of anything. It's just the solution to the three unknowns, all right? And for our purposes, we're really more interested in just what the x's and y's are. Okay? All right. Are we done? Why aren't we done? Hold on, this was finishing off that.
Because you still have y equals 0 and lambda equals, you still have y.
Yeah, so I only looked at when x was 0 and lambda was 2. Another thing I could have done is I could look at lambda being 1, right? So let's try that. A new train of thought here. Suppose lambda is 1. Then equation 1 is good. Okay? But if lambda is 1 and equation 1 is good, the only way to make equation 2 true is to make y 0 because lambda is not 2, right? So y has to be 0. So we're going to let y be 0. That'll take care of our equation 2. And then from that, we can go to equation 3. And that will tell us that x is free this time, y is the one that's fixed at 0, and we can solve that for x, and we get 2 answers here, plus or minus 1. So in terms of an ordered pair, we have 1, 0 this time, and negative 1, 0. In terms of a triple, including lambda, we have this. Okay, so that's x, y, lambda. All right, so we've looked at these two, right? Okay. What about these two? Well, do you all see we've already done these two, right? So we did look at the case where y was 0. When y was 0, we did it right here. That forced our lambda to be 1, so we've already done that. And then we've already also looked at when lambda was 2. That was on this one. So we are now done. We've looked at the only ways we can make the first 2 equations true and got 4 different answers. So now that we have these, what do we do with them? So our points of interest are the 4, right? So now what we need to do is evaluate f, right? So we want to go to our original function f, and then we want to plug in 0, 1, f of 0, negative 1, f of 1, 0, and f of negative 1, 0. Whatever those outputs are, we will look for the max and min. So what happens when you plug in 0, 1? You get 2. When you plug in 0, negative 1, you also get 2. When you plug in 1, 0, you get 1, and negative 1, 0, you get 1. So the maximum value of this function restricted to this circle is 2. And it happens at 2 different places. And the minimum value of that function on that circle is 1, and it happens at 2 different places. And that corresponds to the picture, right? The picture we had 2 places where we had the max. Those 2 right there, and we had 2 places where we had the min. And that's it. That's Lagrange. And now all that happens now is the algebra just gets worse and worse and worse. Okay, your equations become harder and harder to deal with. You start to get lost in, have I covered all the different scenarios? That's what starts happening now. All right? But as far as the method, hey, look, you're just solving 3 equations, 3 unknowns. All right, so let's look at the next example. Find the maximum and minimum values of the function. Hey, same function. Same function. On the disk x squared plus y squared is less than or equal to 1. So what's changed here?
It's now a disk instead of a circle.
Yeah, we're not looking at that circle on the ground. We're looking at everything inside. So the way we do this now is that we break it up into 2 pieces. We do the boundary, which we just did in example 1, right? But then now we need to look on the inside. And to look on the inside, how do we look on the inside? How do we look on the inside? We act like there's no domain restriction. We do this like we're doing this as if we're going to calculate a capital D. So when we did that method, this was what was on the test. When you're trying to find max and min of a function on an unbounded, we're acting like it's unbounded. We take the partial of f with respect to x, set it equal to 0, partial of f with respect to y. We're trying to find the critical points. Right? That's how we find the critical points? Yep. So what is the partial of f with respect to x? We did that earlier. It was 2x, set it equal to 0. That means x is 0. And then the partial with respect to y, which was 4y, set it to 0, and that means y is 0. So the only critical point that I have is the point 0, 0. And this is okay to have now, right? Because this lives in the disk. That wouldn't have satisfied equation 3 from the previous example. But now we're looking not only on this boundary, but we're looking inside of it. So when we find this critical point, we say, hey, does that live in here? And we say, yes, it does, right? And that means we need to check it. So we're going to take this point and plug it into the original function. F of 0, 0 is 0, right? Yeah. So now this problem has a different answer than the previous problem, doesn't it? The answer to this problem is that the max of this function is what? 2, right? And that happened at 2 different places. But the minimum value of this function is what? 0, right? And that happens at this point, 0, 0. So our picture looks different when you look at it. Instead of just having a circle on the ground, we have a disk on the ground. And when that disk gets plugged in, instead of having this curve up on the surface, we actually have a surface again. And what we have found are these 2 highest points. We did find these again, but there's now a new point at the bottom that you can't see. I have to flip it over. There, do you see that point on the bottom? We found that point too. So that's our new minimum. That all make sense? Okay. So that's just going to show you now that we have a way of doing the problems that we had before with Lagrange. Yeah, this one will probably go pretty quick. Find the maximum of this surface with that constraint. What is this surface right there? If you graph it, this is like z equals 4x plus 6y. What is that going to look like when you graph it? A plane, right? So we have a plane, and we're only plugging in points that live on a circle with a radius of square root of 13. So you got some plane, circle on the ground, plug those in. On that plane, you should have something that looks ellipsish, right? Ellipsish, is that even a word? Right, up on this plane. So we should get 1 max and 1 min. Can you all visualize that? Okay, let's see, let's do it. Equation 1. See if we can set up the equations without having to write everything down again. Equation 3. So what's equation 1?
Equation 1 is going to be
that piece right there, right?
yes.
So it's going to be 4, a constant,
Yeah, it's going to be 4
equals lambda times the partial 2x. Okay? And then this next one, equation 2, will be 6 equals lambda times 2y. And then our final constraint here, there we go.
When you take the 2x, move to the other side of the equals, no, yeah. Wait.
I would divide both sides just by 2 first.
Okay.
Just because we can, right? Dividing by 2 doesn't cause any problems. Over here I can divide by 2, I get this. So we've run into a little bit of a problem here because When something is equal to 0, you can set them each equal to 0, but when the two things multiply to be 2, you can't just set them both to 2. So maybe there's something else I can do. So I'm kind of at this point open to suggestions. And if y'all can't figure it out, I'll help you out. But I'll do anything as long as it seems legal and like we're going to make progress.
Either lambda x or y by itself on one side.
Okay, so let's go with that. Let's go with lambda by itself here, all right? The only way to get lambda by itself at this point is to divide by x, which means you need to think about what you are now eliminating from a possible solution, right? So I'm going to go ahead and do this. I'm going to start thinking, suppose x is not 0, all right? Then equation 1 would be able to be written as lambda equals 2 over x, right? Do you all agree with that? So long as x is not 0, then I can rewrite equation 1 to be that. All right? I did what you wanted. Now what? I solved for lambda. Plug it into this one? Okay, you want me to plug that in to right here? Okay. Then equation 2 would then become 3 equals 2 over x times y, right? Can I multiply both sides by x to get this x out of here? Yes, so long as x isn't 0. But I'm living and working under that assumption. So 3x equals 2y. All right? Now what? You want to get y by itself? Okay, 3 halves x equals y. That's all legitimate. Yeah, let's use equation 3 now. Okay, we have a relationship between x and y now, right? Let's go to equation 3. And let's replace, we're going to replace y with this, right? So we'll have x squared plus y, but y is 3 halves x squared must equal 13. And now we have an equation with one variable in it, right? So let's solve this. This is x squared plus 9/4 x squared equals 13. What do we get when we put x squared plus 9/4 x squared?
13.
We get 13/4 x squared equals 13. We can multiply both sides by the reciprocal, and you'll get x squared is 4, and then you get x is plus or minus 2. Okay. So if x is plus or minus 2, then what's y? Yeah, so you have to go through and get y. Y is 3 halves x, right? So now, using that, we know that that means y is equal to, let's see, what happens when we plug in positive 2? We get 3. And when we plug in negative 2, we get negative 3, plus or minus 3. Y'all with me? All right. So let me try and kind of summarize this over here. I got to continue over here, okay? So here's where we're at. Here's where we're at. We know that when x is 2, y is 3. And we know that when x is negative 2, y is negative 3, right? These 2 points should satisfy all 3 equations. Just for the sake of understanding again how important the lambda is, this is really 2, 3 something, and negative 2, negative 3 something. Remember the lambda here, I'm just going to write it in. What would lambda be if x is 2 and y is 3? What's lambda? Do we ever solve for lambda anywhere? We did, right? It was right here. Lambda is 2 over x.